All right. Thank you so much for sticking around. I know it's been a long day of a lot of quantum stuff, so I'm going to shift gears a little bit and talk some quantum. But before I get to that, I want to explore a very different space that we're actually trying to make some difference in. So I'll start by saying my name is Melo. Co-founded a company called Menten.ai about a year ago. And what we're doing is we're looking at proteins, protein design. And just when I say protein, I know it's quite a diverse crowd here. I do not mean the 15 grams of proteins in your cereal bars. Just want to put that out there. Okay. But instead, you can think of proteins as these structures based of amino acids. And turns out they are nature's answer to doing biology, and much more than that. So in this example here, if you can just look at here, that is a monoclonal antibody. Now, this is the kind of structure that our bodies naturally designed, evolved through 4.6 billion years of evolution to target specific pathogens in our bodies and keep us healthy, right? Now, what's striking about such a large structure, in some ways, is its simplicity. It only takes 20 amino acids, and that is the base of it, 20 amino acids. But yet the space of possibilities is ginormous. Just to give you an idea why 20 amino acids, simple but yet complex, is because as these amino acid sequences increase in size, the problem increases exponentially. So in fact, it increases 20 to the n. So just to give you a sense of the magnitude of the problem here, here in this square here, it represents just the space of possible sequences that could exist, okay? Now, nature, over 4.6 billion years of evolution, has only sampled but a very tiny fraction of that, right? In fact, a single 100 amino acid sequence has as many possibilities and more possibilities than there are atoms in the universe. That is a single 100 amino acid protein. And our bodies alone have around 20,000 proteins. So essentially, just the size of the problem is ginormous, right? We have developed some techniques to kind of increase our ability to explore this space. So we can create new proteins to directed evolution, starting from natural proteins. But the problem with that is that if we want to explore something that's over this quadrant, nature hasn't had enough time to even go there. How do we get there? And so that is the promise of protein design. So using these new techniques, we can explore these possibilities from first principles. So we can look at small things like peptide therapeutics, microcycles, vaccines, and all the way to nanoparticle size applications and materials. Now, specifically in the space of therapeutics, the state of the art right now, so what pharma basically does is a very smart way of sampling through huge, large amounts of data. It's a process called high throughput screening, which is essentially trial and error at a massive scale. Now the problem again, even though we can screen through hundreds of thousands, even millions of different compounds, is that the space is incredibly several orders of magnitude larger than that. We don't have enough time in the universe to explore this. Okay, so back to quantum and some computational work. Okay, so the challenge is coming up with a computational pipeline that will allow us to explore this space and look at the different designs that we can come up with. Now, I want to give you a super quick introduction through this pipeline here. Let's assume we have a target, let's say a cancer cell, a specific pocket within that cancer cell that we know is involved in disease. Okay? Now, our challenge is to come up with a molecule that would bind to it. If it binds to it, it could perhaps interfere in the disease and give us a chance of curing or at least treating the disease. And so that is the second step here, the design part. Once we can design it, we can run some simulations, finally have some experimental validations of the process. Now, the problem here, again, is that in the design part, when we're trying to explore this space, is incredibly large. And so the best classical application of that really is just a very simple heuristic, more or less picking in some clever way. Now, if we can use quantum to solve this problem, we may be able to use some quantum optimization, look at the entire possible set of conformations, and allow us to create more accurate designs and actually target the drugs we need, create the drugs we need. Okay. Now, just zooming in a lot more into the actual design part, let's take a very simple example just to give you an idea how this is actually done in practice. So let's say we have a small peptide. This is a small protein, essentially, and we have a number of links here. And essentially what we're trying to do is optimize the structure in such a way that it can conform to specific shape. Now, again, this is a combinatorial optimization problem, and it's hard to do as the problem increases in size. Now, luckily, we can actually express this in terms of energies, so free energy, which allows us to give us a metric to then convert this problem into an optimization problem such that if we can find the minimum or close to minimum energy, we would essentially solve find this optimal structure computationally that we know that we design, we would actually end up with the right molecule. So just to give you a quick sense of what this is like, if we have a small peptide here, we can allow the design of different, positions in that so that we allow these links here to rotate. Now, each one of those links, we can assign an energy to it such that we have a single energy term and an interaction term between the different items. Now, we can further turn this problem into a optimization problem that actually maps really well to an icing problem or a QPU problem. And we can actually pre-compute the energies and just assign them such that we can just worry about the optimization problem rather than the energy of the system. So the way we map this to QAOA is actually fairly simple. We translate into a phase-separating Hamiltonian where we assign every variable, and it just becomes a polysum of the terms. And we can use QAOA, we can prepare our cost function or driver Hamiltonians, and then we just need to initialize the parameters, initialize the different angles, specify the number of steps, and we actually are able to run this problem. And so here is an example of what it actually plays out, what it ends up looking. So we have a conformational landscape. So these are the different possibilities for this molecule this could take. And we parameterize it such that the most likely state is the one with the lowest energy. And so when we run our optimization problem, we're essentially just sampling the energy landscape to see if we can actually find this state or something close to it. We tested this on Aspen 7 using 6 qubits. If we give it enough time to run and we collect enough samples, we can actually see that the low state in this parameterization is actually favored. And we would expect with error mitigation, increase fidelity, and so on, to improve on this on these results. So just to give you an idea of the capabilities of this, in this case, we created a problem such that we allowed 3 positions to be designed. And the interesting thing is that this error coming not from the quantum computation, but actually from the energy function that we fit into it, right? So even if we were able to find the optimal minimum every time, there would still be some error, right? In this case, even the lowest energy point of the solution is actually somewhat different from the actual crystal structure that is found in nature. All right. Now, why does this matter? Why is this important? Well, these are problems for which we know we don't have a good solution. We don't have a good way of solving this in a classical sense, right? Allowing us, being able to design these proteins would enable us to design better stable peptide drugs, monobody and antibodies, as well as improving our capabilities of cell permeability and maybe stabilizing intrinsically disordered proteins. Now, these are actually applications that we are already doing as part of the company, and we hope to improve through quantum methods. With that, I'd just like to thank my team. Vikram Mulligan is one of our co-founders. He's core developer of the Rosetta software package. He's based in New York at the Flatiron Institute. Thomas Gorby, he is a co-founder of the company as well. He is brilliant at engineering proteins and understanding how they actually structure. Finally, Tom LeBeau and David Rivas here for setting me up in QMI and allow me to work on this problem. Thank you very much.